Hello there, and welcome to the series The Basics of Embedded Audio Programming. I am Renato from Guitars AI, and on this tutorial we are going to talk about delay effects. On previous tutorials we are busy looking at how to configure and use different peripherals of the eZdsp and different components of the board, and now we can start focusing on the digital audio processing part, and we will implement a basic delay effect using a circular buffer. So let's get started. Delay lines are fundamental blocks for many audio effects and synthesis algorithms. Here we have a delay line block diagram where we have an input signal xn, and the output is the delayed version of xn by m samples. So a delay by m samples can be written as a multiplication of the signal x of n with z to the power of minus m in the z domain. So here are the equations for these multiplications of the signal x of n with z of minus m in the z domain, and we have this substitution that n prime is equal to n plus m for causal systems. This delay can also be seen as a convolution with the following impulse response in the time domain. So here's the impulse response, and we have m zeros and a 1, so meaning that hn is equal to 1 for n equals to m and 0 elsewhere, and here is in the form of a convolution sum. Here we are going to calculate the frequency response of a delay line when m equals to 3. So here we define our delay operator or our shift operator, so we have 3 zeros and then a 1, and the frequency response we are going to use SciPy signal to calculate with the frac-z. And here we will plot the magnitude of the shift operator of the delay line, and here the phase. So we have a constant magnitude equals to 1, so we don't have any changes in the magnitude, and we have a linear phase for this delay line or this shift operator. We will use this delay line to implement a basic delay effect according to this block diagram. So we have a dry mix part, so we have our input going to a gain for the dry mix and going to the output. We have a wet mix part, which is the delayed version of our signal, so we have this, the delay line, a wet mix gain, and it adds with the dry mix, and this is our output. And we have this feedback loop where the this part here, the signal after the delay line, gets feedback and summed with the input, and here is the signal after the sum, so just before the delay line, and we are going to use this after delay line and before delay line signals also to compute our frequency, our transfer function, and to implement in software. So the transfer function for this block diagram is given by this equation here, where D is the dry mix gain, W is the wet mix gain, and F is the feedback gain, so these gains here. Z to the power of minus 1 is our delay line, and we have this transfer function. So we can analyze this transfer function in a special case. If we set the feedback gains to 0, then we will have this delayed version of our signal and a non-delayed version of the signal. They are added to this output, and this results into a comb filter. So if we set the feedback gain in this transfer function to 0, we end up with a feedback comb filter. So comb filters, they can be used as building blocks of many digital audio effects as well. So let's take a look at the frequency response of a comb filter, this time using m equals to 5. So here I'm defining the parameters, so the dry mix gain equals to 1, the wet mix gain equals to 0, and the feedback gain equals 0, and the wet mix gain equals to 0.8. So we are not having any feedback here, so we have a direct version of the signal and a delayed version of the signal. Then we are setting our denominator and numerator for the transfer function. Once again, we are going to use SciPy signal to calculate the frequency response. This time I'm using whole equals to true, so I will calculate the frequency response from 0 to 2 pi. Instead of 0 to pi, that it's more common for real valued signals, but I just want to show the relation between this m equals to 4 and the computer. So here I am plotting the magnitude of the computer, and here the phase of the computer, and here we see the magnitude of the computer, and we see the 1, 2, 3, 4, 5. So this is the relation I mentioned between the m equals to 5, and if we will just plot until pi, we will not see the 5, but just for visualization. And here we have the phase of our computer. At this point we will have a basic delay effect audio example. So we are going to use the transfer function that we defined here to implement a basic delay effect. So I'm going to use NumPy, SciPy signal, IPython display to listen to audio, and librosa to generate some tones. So here's the function called basic delay, and we have our dry mix, our wet mix, our feedback gain, our delay time in seconds, and our sampling frequency, and this is our input signal. So here we convert the delay time in seconds to the number of samples we want to delay. Here we are defining the coefficients of our filter based on the transfer function, and here we are applying the filter with the coefficients. So it's the numerator and the denominator of our transfer function. So a is 1, a bunch of zeros, and then f. So depending on m, there will be a bunch of zeros, and 1 minus m. So this is the denominator. And here we are generating our input signal that is going to be a 440 hertz. We are going to use 24,000 hertz as the sampling frequency, and this is how it sounds, our input signal. So we have a short tone with 440 hertz. Now I'm going to apply this basic delay that was defined here. So it's filtering the input using these filter coefficients. So I'm setting the dry mix to 1, the wet mix to 1, and the feedback gain for 0.5. I'm setting a delay of 0.5 seconds and the same sampling frequency of 24,000 hertz. So this is our output of this basic delay. So we are using this filter approach. So you can observe that it takes quite a time to calculate. So I will just run this cell now that will compute. So now it's finished, and it's not a very efficient way, but it's interesting to see that we can implement this digital delay as a filter using this transfer function here. So a delay line is often implemented in software using a circular buffer. So a circular buffer can be seen as a type of high performance FIFO queue, a first in, first out, and it's also called a ring buffer. And we can see that there is this definition of circular buffering on this data sheet from another processor by Texas Instruments. So the circular buffer uses pointer manipulation to add new samples to the buffer by overwriting the oldest available samples, reusing a memory buffer. So when the pointer reaches the last location of the delay line, it needs to drop back to the beginning of the line. So this would normally involve some amount of software overhead, and when a circular addressing is used, the pointer automatically drops back to the top whenever the bottom of the buffer is reached. So as a consequence, the memory locations appear to be tied together in a circular manner, hence the name circular buffer. And most digital signal processors implement circular buffering in hardware in order to conserve memory and minimize software overhead. For this example, we are not going to use circular buffer in hardware, but we are just going to use the circular buffer in software. So here we are going to implement a basic delay effect in Python using the circular buffer, but this is a very non-Pythonic style. There are many ways how we can implement this in Python, much more efficient than what I'm doing here. But I'm using this kind of implementation because I want it to be closer to the way I'm going to implement in C to program our DSP. So here we are defining some parameters, the sampling frequency, the delay time in seconds, then I'm converting the delay time in seconds to the delay in number of samples. Here we are creating a buffer with the length of the number of samples we want to delay, and here is an index, so it's something similar to a pointer. Here is the circular buffer itself, so we are using the buffer. So we define it as global variable, so there's a buffer and this index. Here the output is equal to the buffer at the index used by this pointer. Here we are setting the buffer to be equal to the input. Here we are adding 1 to the pointer, so the pointer goes from 0 until the end. And here we have two ways how to set the pointer back to the beginning when it reaches the end. So here we are using an if, so if the pointer is bigger or equals to n, the pointer is equal to the pointer minus n, or we can use the modulus operator, and then when the pointer is equal to n, it will go back to 0. Now we have our basic delay. So here we have our dry mix gain, the wet mix gain, the feedback loop. Here's our input. We're also using the buffer and the index. We are setting an after delay equals to 0. So this after delay is a signal after the delay line, so here, and it will start with the value 0. Then we are setting before delay. Here we are setting just for this example, we are defining an empty list, and we are going to append the output to this list, so we can have our final audio and listen to it. Here before delay is the signal just before the delay line, so it's here, so it's the input signal plus the after delay times the feedback. So this is what I'm calling the before delay. We have here, so it's the input plus the after delay times the feedback gain. Then the after delay is the circular buffer of the before delay, so it's basically the after delay is the delay line applied to the before delay. And the output will be after delay times the wet gain plus the input times the dry gain. So we have here is the input times the dry gain plus the after delay times the wet mix gain. And then we are just appending to this empty list so that I can have here our delay and listen to it. So here I'm applying this basic delay to the delay input is the same we used here. So this is the input signal, and now I apply the delay, and this is the output. What we see is the same output as before, but now when I run the cell, you'll see I'm running. First I need to run the previous cells, and it's much faster than the filter version that we had here. It took much longer. Here we just run, and that's it. It's already calculated. So we are going to use this kind of implementation, but adapting it to the C language to program our DSP. And here will be our basic delay effect on the C5515 DSP board. So there will be this file, basic delay, and we're defining here a buffer with a max buffer length. So in our case it will be a 0.5 seconds. Here I am defining an auxiliary function to convert seconds to samples. So if a person tries to put a value higher than 0.5, it will limit to the max buffer length, which is our buffer is defined to have a maximum of 12,000 samples, because we are using a sampling frequency of 24 kilohertz. And if it's a value smaller from 0 to 0.5, we convert these seconds to number of samples. Here is our delay line, so it's very similar to what we did in Python. So we have this index, we have the delay buffer defined here that we're going to use. We are using this modulus operator. We are doing exactly the same thing what we did before. And here is our basic delay effect, and we are using our delay line or circular buffer. We have again our before delay and after delay, and then we have our outputs is the after delay times the wet mix plus the input times the dry mix gain. And this is how we are going to implement on the C55 eZdsp board. Here I am on the Code Composer Studio, and we have our basic delay effect. So the thing you need to do is the same like before. You start a new project, then it will create this folder, and you copy the files from the zip file to the folder. Then we'll have all this. So if we take now a look, we have this basic delay, and we are defining this maximum buffer length is 12,000. Here is our delay buffer. Then we have this is a function to clear the delay buffer. So later on, if we want to vary the amount of delay up to the maximum, so if we want to delay not by 12 samples, but we want to 12,000 samples, but we want to delay to 6,000 samples, we can do this by changing some parts of the code. But it's good to have this possibility to clear the buffer before we change the value of the delay. We are not going to do this on this example, but this function is already here. Here is the function to seconds to samples that we discussed it before. Here is our delay line, and here is our basic delay effect. Here is the header file for our basic delay, and here on the main we see is very similar to the previous example. I still need to change here because now we are on the delay effect. So we have this basic delay effect. We have some welcome message, that is tutorial 5, and it will be that the first state is converting from stereo to mono, and the second state is the basic delay effect with 0.5 seconds. So is this the same like we did before? We use this push buttons, so you can change the state by pressing the switch push button 1 and 2 for up and down, and you can reset both pressed at the same time. Here we convert from stereo to mono, So if the state 1 we just have stereo to mono, and on state 2 we are calling our basic delay effect, the mono input, and then the values. We have the dry mix gain, the wet mix gain, the feedback loop gain, the delay in seconds, and the sampling rate. So this is the example for the basic delay, and you can build the project. So here the console we have the build, and we don't have any problems, any errors, and then we can run this on the board itself. So now I have my guitar connected to the board. We can go to run, debug, and the program is ready to run from inside the main. You can run. We see there is this welcome message, guitar tutorial 5. So now we have this stereo to mono. So if I play, so there is no delay, just the stereo to mono. Now I'm going to go to the delay, and we have our delay. And back to so that's it. This is the end of our tutorial, and we implemented a basic delay using a circular buffer.